Turbo machines. We have three types of turbo machines. We have pumps, turbines, and everything else. These are blowers, fans, and compressors. Pumps use mechanical energy to add energy to a fluid. Turbines are the exact opposite of pumps. They use fluid energy to add mechanical energy to a system. Blowers, fans, and compressors are similar to pumps in that they use mechanical energy to add to fluid energy. Let's talk specifically about pumps. When we select a specific pump, we need to understand the performance characteristics. The top characteristics that we look at are the work done by the pump, the actual head that the pump creates, and last, the pump efficiency. All of these values, work, head, and efficiency, have a relationship to flow. As the flow increases, the head is going to decrease. The work is going to increase for the most part, and it comes back down. And the efficiency has a peak point here before it starts coming back down. We call this peak point right here the BEP, or the best efficiency point. In a lot of cases, the best efficiency point is the flow rate we want the pump to be running at, because that is going to be the most efficient under work and head conditions. Manufacturers will provide performance curves similar to this one, 416 in your textbook. The pump in this case has an assumed efficiency or a constant efficiency and a constant impeller speed, omega O, of 1750 rotations per minute. So that's why the efficiency curves look really funny from the previous one that I drew up here. Now the head is still in blue, but this time it is for 3 different diameters. So depending on what we hook up to the pump, we will have a different head produced by the pump running at this speed at that efficiency. Okay, so let's say, for example, we have a 6-inch diameter impeller, okay, and it's going to be most efficient over here at 86%. Okay, so that's where it crosses because we've got this circular pattern for our efficiency. So coming down here, that's a flow rate of around 470. Coming back over here on our head, we're going to be around 140 based on my lines here. And the red lines are our horsepower, and we're just past the 20 horsepower. So I would say, 20 and a half, 21 horsepower for that pump power requirement. Here we have 2 tanks that are connected by a 100-foot long 3-inch diameter pipe that has a friction factor of 0.02. The first tank on the left has a 5-foot depth, and then there's the pump here that has a 6-inch diameter impeller. And then from the bottom of tank 1 to the water elevation of tank 2 is approximately 115 feet. We want to find the flow rate between the 2 tanks and use figure 14-6 for our pump information. So if I'm looking for flow rate between 2 tanks, I'm thinking energy equation. So we'll call this tank 1 and this tank 2. Both of the tanks are open to the atmosphere, so our pressure is going to be 0. Both of them are reservoir tanks, so I'm not going to have any velocity. I do not have a turbine. And if we set the datum at the top of tank 1's water elevation, then that puts Z2 at 110 feet. Remember that head loss is equal to friction L over D plus KL times V squared over 2G. We're going to neglect minor losses because this is a 100-foot pipe, so friction losses are going to far outweigh the 2 little bends that we've got drawn there. So we're going to plug that into here, and this equation is going to clean up to solving for the pump. Our pump equation here with the elevation of 110 feet and then our major friction losses. Multiplying this out, I have my pump to be 110 plus 0.12422 V squared. Now I'm asking about flow rate, and if I go to figure 1416, the plot is for head and flow rate. So let's put this equation into flow rate. We are dealing with water, which is incompressible, so Q is equal to VA. V times pi over 4 times 3 inch divided by 12 inches per foot squared. And that gives me a flow rate of 0.04909 V. Plugging that back into my pump equation, I have 51.554 Q squared. To replace that 0.12422 V squared. Now I have the pump head in terms of flow rate, and I can look at figure 1416. In this figure, we want our head and flow rate to fall along this blue line, and we have neither. So I need to take a guess at a flow rate to get to a pump head, and then once I find one that's about on that line, that's going to be the Q and H that I use. The most efficient flow rate I can have is 470 for that 6-inch diameter impeller. So I'm going to start with that guess, 470. Remember, 470 is gallons per minute, and our equation here is set up in feet and seconds. So doing that conversion, I get 1.047 feet cubed per second, and plugging that into my head equation, I get 166.5 feet of head. So when I come over to my graph, 470, let's see, this is 50 right here. So 166 is going to be somewhere up there. We are a little too high. So let's slow our flow rate down. Let's go down to the next line, which is 400. At 400 gallons per minute, I get 151 pump head. So coming over here, 400 to 150.1. Hey, that's good, and it falls just over 80%. So we are on our 6-inch diameter impeller line. So we are going to go with a flow rate of 400 gallons per minute. Here we have a similar question where we have 2 reservoirs with a pump. The pump is represented by this diagram over here with head to flow rate. I have water at 20 degrees Celsius. The pipe is 50 meters long with 50 millimeter diameter galvanized iron, and it has 5 elbows. So those 5 elbows tell us that we need to remember to consider our minor losses. Find the maximum flow in the pipe. Now this is going to start out the same way as that last problem with the energy equation between 0.1 and 0.2 and I'm going to set 0.1 as my datum. Once again, we have two open reservoirs, so there is no pressure and no movement. I do not have a turbine, and Z1 is my datum, which means the pump has to only overcome that elevation Z2 and my head losses. My pipe has 5 elbows, so going back to chapter 10, I find that my KL factor for an elbow is 0.9, so I'm going to have 5 times that. Then all of my coefficients here for major and minor losses, I'm going to multiply to velocity head v squared over 2g. Now this time I have 3 unknowns. In the last example I was given a friction factor. This time I'm not. So we're going to have to do even more guessing and iteration than we did the last time. But first, cleaning this up, our pump head equation expands out to this mess. What is that? 13,220,306 friction flow squared plus 59,491.4 flow squared plus 8. Moody diagram needs the roughness factor and Reynolds number. I was given galvanized iron, so our E over D value for the Moody diagram is going to be 0.15 millimeters over our diameter, 50 millimeters. And that gives us 0.003. Our Reynolds number, VD over nu. I do not have velocity, so that's going to be 509.296 Q times 0.05 meters all over the kinetic viscosity of water at 20 degrees Celsius, which is 1 times 10 to the negative 6 meters squared per second, according to the Appendix A in the back of your book. With our Reynolds number in terms of Q, we can use that with our roughness ratio to get a friction factor to calculate a head, and then see if we can merge on the graph like we did with the last one. So starting off very simply with Q is equal to 1, I'm going to have 1, 2, 3, 4, 5, 6, 7, 2.5 times 10 to the 7th. So that's going to be here, coming up here to 3, which is about in the middle. Then drawing a line over to my friction factor, I'm going to get about 0.026. So let's see. So plugging in my flow rate of 1 and my friction factor of 0.026, I get a pump head of 403,227.4 meters. So our Q is a little bit high, but 1 was an easy number. So let's keep the 1, but let's add some more zeros in front of it. 0.01. Using a flow rate of 100ths meters cubed per second, I get a Reynolds number of 254,648, which gets us to about right here on our Moody diagram. And that brings our friction factor up just a tiny bit. So I can say that's about 0.0256. I mean 265, right? Yeah, it's about in the middle there. That gives me a new pump head of 49. 48.983 for those of you that want a little bit more significant digits. So this we can actually put on our diagram here. So at 0.01, we're about right here. All right, so 0. So we need to choose a larger value here. And by the way, yeah, this is kind of an indicator that I shouldn't have started with 1, but the point was easy math, not logical math for that first try. So let's bounce up here to 0.025. At a flow rate of 0.025 meters cubed per second, I get a Reynolds number of around 64,000. So that gets us over here to this part of the Moody diagram. And you see that we're kind of honing in on a friction factor. So we're bouncing between 0.025 and 0.027. So that's nice that we're staying about there for our friction factor. Plugging the friction factor into our equation, I get a pump head of 251.7 meters. So yay, quite a bit of a jump. So coming over here, 250. So that gets us right about there, okay? So you can see this curve come in here. And this is what we're trying to reach. So what is that? That is about 0.035. So let's give that a shot and see if we get a head around 450 is what we're looking for. This time I calculated a head of about 501. That's going to be a little high, so let's bring it down 0.032. At a flow rate of 0.032, I get a head of about 420. So I've come up here, I've edited my plot a little bit because at that 35, we were up here at 500. So that brought up my curve a little bit. And then at 0.32, which is about in the middle of this 0.03 to 0.035, that's about here, 420. So I need something in the middle. I'm going to call this my last iteration, and I'm just going to take an average of the two, which is going to be 0.0335. Notice my friction factor has really been honing in on that 0.026. I get 461 this time for my pump head. That's much prettier, fits on my graph a little bit better. So I'm going to go with a flow rate of 0.0335 meters cubed per second as my answer for this question. One crazy thing about designing for pumps is the net positive suction head, which we need to check for cavitation. Cavitation occurs when the liquid's pressure falls to or below the vapor pressure of the liquid. And this often happens on the suction side of the pump. So we need to make sure that that net positive suction head is at least equal to greater than the liquid's vapor pressure. So we don't have cavitation. So vapor pressure, we're going to put into pressure head, specifically vapor pressure head, which is going to be PV over gamma. Next, we need the critical suction head. And the critical suction head is the absolute pressure and velocity head coming into the pump. So that is pressure over gamma plus V squared over 2G. Net positive suction head, we don't want that to be 0, right? So that's our last equation. The net positive suction head we can calculate on the system is going to be the critical suction head, P over gamma, plus V squared over 2G minus that vapor pressure head. This is the additional pump head required to move a liquid through the pump. So here we have a reservoir with 80 Fahrenheit water, and it's being sucked out through an 8-inch diameter pipe through a pump at a flow rate of 2 cubic feet per second. Find the net positive suction head and neglect major losses. My net positive suction head equation is the critical suction head, so that is P over gamma plus V squared over 2G minus the vapor pressure head. So to get the critical suction head, I need the energy equation. And I'm going to take it from the surface of the reservoir to just before the pump. Setting up the water elevation as our datum. I'm going to have 0 elevation here and an elevation of 6 feet here. This is just before the pump, so there's no pump head here, no turbines. Okay, now normally, because the tank is open to the atmosphere, pressure is 0, but we want absolute pressure, so it's not going to go to 0 here. This portion right here, just before the pump, that of course is our critical suction head. Head losses, we were told to neglect major losses, but we've got 2 minor losses we're going to take into consideration. V1. Still is not going anywhere, so no velocity 1. Let's plug in our known numbers. 14.7 is in PSI, so let's multiply that by 12 inches per foot squared. We're going to get P2 over gamma plus V2 squared over 2G is equal to 27.3 feet. Going to Appendix A, we get our vapor pressure for 80 water at 0.507 psi. So that means our net positive suction head is equal to 27.3 feet minus 0.507 psi all over 62.4 pounds per foot cubed, and we'll need to convert again. 12 inches per foot squared. Our net positive suction head is equal to 26.1 feet. So that is the head that our pump needs to overcome in this system. If we have pumps that are the same type and we wish to compare them, we can use pump scaling laws or turbo machine similitude. We're going to talk about 3 different options. The first one is flow coefficient. So that is our flow rate of one pump and the impeller speed and the diameter of the impeller cubed. And that can set equal to our other pump's flow, its impeller speed, and its diameter cubed. We also have head coefficient. So that'll be the head of pump 1 over the impeller speed squared and the impeller diameter squared, set equal to the other one. And our last similitude coefficient is power. So that's the pump power 1 over the impeller speed cubed and the diameter of the impeller to the 5th equal to the power of the second one, its impeller speed and diameter. All right, what if we have a pump that needs 28 horsepower to run at 1750 rotations per minute? And we want the impeller to now run at 630 rotations per minute. How much power is it going to need? All right, so looks like we're going to need to set power equal to each other. Now our units are going to be the same on both sides. So if we start with horsepower, power to begin with, then we're going to end up with horsepower at the end. So I'm not going to worry about conversions. Also, this is the same impeller. So that means the diameter remains the same. So these two values are going to divide out. So I will have 28 horsepower over 1750 rotations per minute cubed. And I need to set that to my new horsepower over 630 rotations per minute cubed. And I get my horsepower to be 1.31. This time I have a model of a water pump with a 4-inch diameter, a flow rate of 80 gallons per minute, and a 4-foot pressure head. I want to find the diameter of the prototype with a 600 gallon per minute flow rate and a pressure head of 24 feet. So I'm going to need flow coefficient and head coefficient because I don't have any impeller speed. So I'm going to need to use these two together to get the diameter that I need. Rearranging my flow coefficient to get the impeller speeds on one side, I get flow 1 over flow 2 times diameter 2 cubed divided by diameter 1 cubed. I'm going to do the same thing on the head side. Isolating my impeller speed on the head coefficient, I get the square root of h1 divided by h2 times d2 squared divided by d1 squared. Now I can set them equal to each other and plug in my known values. I set all the 1s as the model and all the 2s as the prototype. And when I solve for D2, I get approximately 6.9992 inches. So I would say our prototype needs a diameter of 7 inches.